So these two new shapes are very much connected to sine and cosine, but so they have some things that are similar, but a few key differences that make them have a unique shape. So I want to start with what they have the same. So let's think about the cosecant graph, CSC. The cosecant graph uses the same 5 dots that sine does. So that's the nice thing. You already know sine of x, and so the same 5 dots that are used for sine of x are used for cosecant of x. Also has the same amplitude, has the same period. And so those things are the same. For secant of x, it uses the same 5 dots as cosine. So if you know those 5 dots, you're all set. And also the same amplitude, same period. But the difference, okay, so what if that's what's the same, then what makes these graphs different from each other? All right, so I'm going to do next to this, I'll do what is different. They have different domain. They have different range. And the dots are not connected. So what makes a sine graph a wave is that the dots are connected. High connected to medium, connected to low, back to medium, up to high. For secant and cosecant, their dots are not connected, which means they're separated from each other. So let me show you how to draw this and show you what we use the same, but then how they end up being slightly different. Okay, the first one I want to do with you is the graph of 2 cosecant of x. All right, 2 cosecant of x. Okay, cosecant uses the same 5 dots as sine. So go ahead and put the 5 dots for sine on there, using your spacing being every 4, like we'd done earlier, just to give us some space to work. All right, so just don't connect the 5 dots. Then label your scale. Amplitude is 2, which means our low value is -2. Our period is still the same. The calculation of the period is 2 pi divided by b, which works out to be 1. Excuse me, b is 1, so our period is 2 pi, so we have 0 pi at the beginning. The end of the cycle is 2 pi. The center is 1 pi, and then half. All right, that's the part that's the same. Here's where it starts to be different. Switch to your highlighter feature. And we're going to use our highlighter to construct asymptotes. Asymptotes are invisible lines that form a boundary and break a graph into pieces where the graph can't cross that boundary line. There is an asymptote at every dot that sits on the x-axis. So what's the first dot to sit on the x-axis? Okay, so there's an asymptote that comes through there. Then there's another asymptote at the next dot that crosses the x-axis. And then another one. And the pattern of asymptotes just keeps continuing on and on and on. This forms your domain. The domain used to be all real numbers. The domain is not that anymore. The domain is all real numbers except so all real numbers not equal to. And it's not equal to the position of the asymptotes you just drew. And so I'd like you to list me at least 3. So 0 pi, 1 pi, 2 pi, and then we usually write dot, dot, dot to show that we are continuing that pattern over and over and over again. So the domain will not include any number that is equal to an integer and a value of pi. That's how you write domain. It's connected definitely to the asymptotes. All right, then, well, what do we do with our amplitudes? Our amplitude that's above the x-axis, the positive amplitude, the graph looks like this. It's a U shape. We call that a branch. And it has to stay between the asymptotes. So your asymptotes act as the boundary lines, which keep that branch in between. And so that has its own range. We call this the upper range because it's above the x-axis. Okay, the upper range. And we write it as, well, what is the lowest number of that section that I just drew? 2. Less than or equal to. And what's the highest number of that piece? Infinity. And so when you write infinity, remember you don't put the equal to bar underneath. It just is less than infinity. But then what do I do with that last dot? Okay, that forms kind of a mirror image, and it is a branch that is facing downwards. Okay, and that branch has its own range as well. That's called the lower range. And so the lower range goes from, well, what is the lowest of that one? Well, the lowest of that one is negative infinity, less than y, not less than or equal to, just less than y. And then the highest of that stops at negative 2. Okay, and that is the graph of cosecant. And then that cycle continues over and over and over again. And so if you were to draw additional pieces of this graph, you would have another upper branch followed by an equally spaced lower branch, and that cycle just continues over and over and over again. Okay, this is the reciprocal graph of sine. Okay, if I had drawn sine on this graph, it would have fit like that. Okay, sine fits between the two branches of cosecant. The only places they have in common would be where they would intersect. Okay, so sine isn't, we're not drawing sine, I'm just showing you that it fits in between those two things. Okay, any questions on cosecant? So if you can draw the 5 dots for sine, then you can draw cosecant. All right, let's try another one. Next one I'd like to do with you is y equals secant 2x. All right, well, we just need the first 5 dots of cosine. So my first 5 dots of cosine are shaped like this. So same 5 dots. The labeling is exactly the same. The amplitude is 1. What's the period for this one? It is 1 pi. So when I label my x-axis and go out to 1 pi, then the middle is 1/2 pi and 1/4 pi, and then 3/4 pi. Okay, that's where the similarity ends. Now I'm going to form cosecant the exact same, or secant, excuse me, the exact way I formed cosecant. I'm going to switch to my highlighter, feature so I can build my asymptotes. My asymptotes still are every place that there's a dot on the x-axis. And so my first dot on the x-axis is at 1/4 pi. My next dot on the x-axis is at 3/4 pi. I'd like you to have at least 3 asymptotes drawn, so you'll have to add another one on there. So you just keep following the pattern. We need another dot, spaced 4 dots apart, switch to that, spaced 4 units apart, and so my next asymptote would be out at the end. Or you could do an asymptote on the negative side. That would be fine as well. There's an asymptote 4 units back that way. As long as everything, what's the total amount of spacing between the asymptotes themselves? Should be 8. Or yeah, okay, 8 counts in between. Okay, so then that affects how we write our domain. And so our domain is written all real numbers except, and then I want you to list for me at least 3 of the asymptotes. So I know that the first asymptote was 1/4 pi, and then 3/4 pi, and then I need you to list me at least another one, okay? 3 would kind of be the minimum. So give me the name of one of the other asymptotes, either the one where I went farther on the positive section or one where I went backwards to the negative section. 5/4 pi, sure, that would be the positive one. So you're following the pattern of odd numbers, 1/4, 3/4, 5/4. You could predict 7/4 would also be in that, 9/4. But it also works to go backwards in the negative section. I could also say -1/4 also. And then put dot, dot, dot to show that the domain is extensive, covering all of those asymptotes. Then you're ready to draw your branches. The branches are very similar to the cosecant branches. The upper branch is squeezed between those asymptotes, and there are multiple upper branches, infinitely many of them. Those upper branches have an upper domain, an upper range. And so my upper range is 1 as its lowest number, less than y or equal to y, and then less than infinity. And then my lower range is squeezed between those asymptotes. There are infinitely many of those also, but all of those lower ranges have the value of negative infinity as their low and -1 as their high value. Now it is possible to shift these graphs side to side or up or down. It's also possible to reflect them. If there's a negative, then the 5 original dots are reflected upside down. Or if there's a shift side to side, those 5 original dots are shifted side to side or up or down. It is possible to shift all of those. So if I shifted this whole thing, say, up a couple units, that would affect the upper and lower range. It doesn't affect the asymptotes, but it would affect the upper and the lower range of where you would end up drawing those. Okay, if you pulled this up higher, the upper range would go higher, but the lower range would go higher also. So let's say we pulled this whole thing up 2 units. Okay, if I decided to do that, I'll switch colors and I'll draw it in green. Okay, if I pulled that thing up 2 units like that, it would have a new upper range. Instead of its range being 1 to infinity, its range would be 3 to infinity. But if I pull the lower one up 2 units, that's going to pull it above the x-axis, so it would be up like here. That's going to pull the lower range up as well, so it would still have a range of -infinity, but its highest level would now be at 1. and so it would be now above the x-axis if I pulled it up. So the range changes, but not the domain. The only thing that would change the domain is if your asymptotes moved side to side onto a different location.